Let me start off with just something to remind you. Suppose we have a vector space. Suppose you have a vector space, and you have a basis. Okay. What is the coordinate vector of the vi with respect to the E basis? So just to get you warmed up, thinking in the right way. So just to remember coordinate vectors. So think about it for half a minute, and then we'll talk to somebody. Okay, talk with somebody nearby. Okay, so anybody have an idea? Anybody have an idea? Stella, how about you? You're smiling? No?
I don't know the exact answer to this, but I kind of know that the coordinate of the VE times the
The coordinate, say it one more time.
the VI responding to the E basis times the E basis
Equals.
the V vectors.
Okay, so let's see. So just to set up things, right? We've got our vector space, right? And then we've got our n down here, right? And you start off with some vector up here, and then you have some sort of corresponding vector in Rn down here, right? Remember what these coefficients are, right? How do you get the coefficients? How do you get the coefficients? Well, you say you express V as a linear combination of, you express V as a linear combination of these guys, right? And then you take those coefficients and put them into a vector. Okay. Okay. So what if we have VI? So let's say V1. Okay. What's the coordinate vector of V1 with respect to the E basis? This is actually easy, so don't be afraid. How do you first you say, well, I want to express V1 as a linear combination of these guys. Well, what is it? What's a linear combination?
1, 0, 0.
1, 0, 0, right? So you're going to take 1 of the first guy, 0 of the second guy, and 0 of everybody else, right? So what's its coordinate vector? The coordinate vector of V1 is going to be, well, just those coefficients, 1, 0, 0, 0, 0, 0, right? The coordinate vector of V2 is going to be 0, 1, 0, 0, 0, 0, 0. Right? The coordinate vector is V3, etc., right? So you see that VIE is going to be just the standard basis vector, right? It's going to be the standard basis vector with respect to I. The ith element of the standard basis. Okay. Everybody okay? I'm hoping that that should be pretty clear to you. Okay. Okay. So now let's get back to where we were. Okay. So remember where we were. We were talking about matrix representations of linear transformations. Matrix representations of linear transformations, right? And so what do you have? You have some linear transformation going from one vector space to another, right? And you have two bases. So you have a basis v1 through vn, a basis of v. You have w1 through wm, a basis of w, right? So this is what we set up last time. You have the coordinate vector maps, right, going from there to there, right? And so I think we call these guys P and Q, the coordinate vector maps, right? And can anyone tell me what the matrix representation was? What was the point? That you're given all these things and you can get some matrix A. And that matrix A did something. Right? Yeah, Julia.
So when you left multiplied the original matrix by the matrix A, you would get, or if you left multiplied in the basis V by the left, or left multiplied by A, you would get it in the map, the coordinates mapped to the basis W.
Yeah. So it was stated in kind of a funny way that if you start off with a vector here and put it with respect to the E basis, this is what I think you're saying. If you start off with a vector here and look at its coordinate vector with respect to the E basis, and then left multiply that by A, then you get the same thing as if you took that vector, mapped it over to W through T, and then took that thing's coordinate vector with respect to F. Okay, so so there exists an A such that this happens, right? And this guy is called the matrix representation. The matrix representation of T with respect to E and F. Okay, right? And we hadn't shown how you get this matrix. We just said that such a matrix is going to exist. Okay. So why does such a matrix exist? Why does such a matrix exist? Okay. So we'll do a proof by construction, just like we did last time. We're gonna make the matrix. Okay. So we construct it. Construct A as follows. Let A be the matrix whose columns are, as usual, denoted A1 through AN, where the ith column is, what do you get when you take the ith element of your basis, you take the ith element from the E basis, map it over, and take it down. Okay, so you take each element of your basis, map it over and take it down, and those are your columns, right? Take the first element, map it over, take its coordinate vector, that's your first column. Take the second one, map it over and down, that's your second column, and so on and so forth. Okay, that will give you something like this. Okay. So Okay, so then, I claim this is the A we want. This is our desired A. Okay, so what do we need to do to show it's the right A? We need to show that it does this, right? We need to show that it has this property. Okay, everybody all right? Okay, so let me rewrite this. I'm going to write this like this. We need to see that AVE equals TVF. Okay, I'm going to rewrite that. That's the same thing as saying that T sub A PV equals QTV. Okay, does that make sense? Does that make sense that these two are exactly the same, that this thing and this thing are the same? Take a look, right? So P is the coordinate vector map, right? So PV is V with respect to the E basis, right? Right, so this thing here is V with respect to the E basis, right? Because P is the coordinate. We're using P for the coordinate vector map here, right? Okay, so all I'm saying is that T sub A VE, well, T sub A VE is, of course, A times VE, right? Right, T sub A means left multiplied by V, by A, right? Okay, over here, right, we've got TV, and then we take Q of it. What's Q? Q is the coordinate vector map with respect to F, right? So this is the coordinate vector with respect to F of that. Okay, right, so these things, right? So you see that these two are exactly the same statement. I'm just changing the notation a little bit. Okay. Everybody okay? Okay, good. Okay, so we need to see that these things are the same. Well, let's consider TAPVI and consider QTVI. Okay. Let's do the second one first. Consider QTVI. QTVI. Well, QTVI is just TVI, the coordinate vector with respect to F, right? The coordinate vector with respect to F of TVI, right? That's AI. Is this everybody following what I'm doing here? Watch for a second, please. Okay, so right, TVI. This in case you're confused, this is a composition, right? You're taking Q of TVI, right? Is it Q of TVI? Well, Q is. Remember what Q is? Q says take the coordinate vector with respect to F. Okay, So it says, well, take the coordinate vector with respect to f of t vi. So that's what that is. That's easy. Okay. What about ta p vi? Ta p vi. What's that? I'll give 2 points on the exam to the person who sees what it is first. And can figure it out. It's Zian, too fast. Wait, don't say it. Okay, I want everybody else to think too. So people try and figure it out. So think, what's PVI? Anybody else figure it out? Stella, you were smiling. Did you figure it?
I got TAVI. VI with respect to the E basis.
Okay, so TA VI with respect to the E basis. Can anybody go a little bit more than that? Slowly? Actually, Julia, you were looking at me first.
Is left multiplied that by A.
Yes. Molly?
And then I said that mapped it to WI with respect to F.
What's W?
When we map it across.
Oh. No, actually. Yeah. Yeah, not necessarily. Anybody go farther? Stella?
AVI equals to TVF corresponding to. Oh, we need to prove that.
That's what we're trying to show. Yeah. So yeah.
Since that's a left-hand multiplication of VI and the E basis, it's that we can show that that's the VI and the F basis.
Okay, so nobody's got it actually. Yeah, Kaki.
Since VIE is like the standard coordinate vector,
Exactly.
it's multiplying that one column in A.
Great. So VI with respect to E is E sub I, right? We said that, we noticed that at the very beginning. And so when you take a matrix and multiply EI by it, what do you pick off? Kaki, you want to finish it?
Oh, it's just going to be AI.
AI, exactly. You get it. Okay, so you get AI. Okay, so you get AI. So, in other words, so TAP VI equals QT VI for all I, right? So, so they agree on a basis, right? So TAP equals QT since they agree on basis. People get this? It's a little bit, maybe it's a little bit hard, but right. We're looking for the matrix. We're looking for the matrix that makes this happen, right? We're looking for the matrix that makes this happen. This, in alternate notation, is just this. in alternate notation, that's just this. Okay. Well, we create this matrix. We create the A matrix. Right? We create the A matrix, and we see that these two, we see that QT and TAP agree on the VI basis, on the E basis. Right? And so these are equal. That's it. Okay. So we build the matrix like this, and if we do it that way, then we get this agreement. Okay. So this gives us the way of constructing the matrix representation. So the way you construct the matrix representation, you see, is that you take your E basis, you map it through the linear transformation, and you take its coordinate vector with respect to the F basis, and you use those guys as the columns of your matrix. Okay. Okay. So to construct, just pulling out this little bit of the proof here, to construct A, the matrix representation of T with respect to E and F, we let the ith column of A be the we take the ith element of E. We take the ith element of E, map it through the linear transformation, and take its coordinate vector with respect to the basis on the other side. Okay, so let's go back to the example that we had the other day, where V was P3, and W was P2, right? And we had basis 1 x squared and basis 1 comma x, and T was the differentiation operator. Okay. So what is A? Don't look back in your notes. I know it's in there, but take a minute and see if you can construct A following this procedure above. Okay. Take 1 minute and see if you can construct A. Don't look back. While you're doing it, pass back some homework. Okay, talk to somebody nearby about what the matrix is. How do you do it? Somebody want to tell me how to do it? What do you do? Yok, you looked at me? So take a look. I'll make you do it. Okay. I'll lead you through it. To construct A, we let the ith column. We get the ith column by taking the ith element of the first basis and mapping it through the linear transformation and taking that the coordinate vector of that with respect to the second basis. Okay. So to get the first column, we take the derivative of the first element, right? Take the derivative of the first element, and then take the representation of the coordinate vector of that with respect to the second basis, right? Well, what's the derivative of 1? 0, right? So now what's the coordinate vector of 0 with respect to this basis? Well, you need to find the coefficients. Well, so 0 is 0 of 1 and 0 of x, right? So what's the coordinate vector? 0, 0, right? So the first column is 0, 0. Okay, simple, right? You tell me the second column.
So it's going to be 1, 0.
It'll be 1, 0, exactly. Right? Because you take the derivative of x, that's 1. You take the coordinate vector of 1 with respect to 1x. Well, that's 1 comma 0, right? So you get 1, 0. Okay. Somebody, Dan, how about you give me the last column?
You take the derivative of that, which will get you 2x, and then you need 0, 2.
Exactly, 0, 2. And if everyone goes back and looks in your notes, you'll see that that's the matrix that worked. Okay, and that wasn't a mystery. It wasn't by chance that we did that. Okay, everybody get that? Everybody get that? How do you construct the matrix representation? Well, you just take the elements of your first basis, map them through the linear transformation, and take the coordinate vectors with respect to the second basis, and use those as your columns. Okay. Let me put up another one, just to consolidate that. So let S be the span of e to the x, x e to the x, x squared e to the x, and D be differentiation. So D goes from S to S. Okay. So find the matrix representation of D with respect to the basis e to the x, x e to the x, x squared e to the x on both sides. Okay, so we're going to use the same basis. We use the same basis. We use the same basis on both sides. Okay. So take a minute and just start this off, or finish it if you can in that 1 minute. But don't take too long. At least get the first column. Try and get the first column. If you get the first column, you probably know how to do it. Okay. Turn to somebody nearby and talk about how you do it.
So, 0 which is
The first column you just do
X
Okay. Somebody tell me how to get the first column, or somebody tell me the first column. Julia? No? Lizzie?
0, 1, 0.
Is it 0, 1, 0? I don't think so. Somebody else? 1, 0, 0? Yeah, actually it's 1, 0, 0. Okay, so how do you think about that? That's okay. If it were me, I would not even say a word. That is, if it were me as an undergraduate, I would probably not even be brave enough to say anything. So the fact that you all can say things in class is a miracle to me. Okay, so how do you get the first column? Well, you take your it's going to be, you take d of your first element, right? And you take the the coordinate vector of that with respect to the basis, right? Well, the derivative of e to the x is just e to the x, right? And you say, okay, how do I represent e to the x as a linear combination of these guys? Well, it would be 1 of this guy, 0 of this guy, and 0 of this guy, right? So you use those coefficients, you get 1, 0, 0. Okay. Right? If you want the second column, you take the derivative of x e to the x, right? Which is the first guy times the derivative of the second, plus the derivative of the first times the second. Take the coordinate vector of that with respect to e, right? And you see that that's going to be 1, 1, 0, right? 1, 1, 0, right? And the last one turns out to be A3 turns out to be 0, 2, 1. Okay. Any questions about this? Any questions?
Actually, yeah. So
Yes,
can
yeah.
we just go over what it means that we're doing here? We're saying
We're creating a matrix that contains all of the information of the linear transformation. We're creating a matrix that, so here's S, and D. Now we've got our coordinate maps that go down to R3. Okay, we've got our coordinate maps that go down to R3, and what we're doing is we're creating a matrix that we can use to map from R3 to R3. Okay, in such a way that the way that this matrix acts on R3 to R3 mirrors the behavior of D from S to S. Okay, that's what we're doing. We're creating a mirror in the Euclidean world of D's action in this non-Euclidean world. Okay, that's really more poetic way of saying it. Okay. Right. Yeah, it's like they're the same things, just in different universes. Okay. Yeah, and so this thing turns out to be there's A 1 0 0 1 1 0 oops 1 1 0 0 2 1 turns out to be the thing that acts like differentiation over here. Okay. Okay. Let me just try to make this a little bit more clear, Nico. So, if I take x e to the x and I differentiate it, I get x e to the x plus e to the x, right? Okay. If I take x e to the x and take its coordinate vector with respect to this, if I take x e to the x and take its coordinate vector with respect to this, well, that's 0, 1, 0, right? Now, if I take that guy and hit it with A, so I take A times 0, 1, 0, you see what I get is 1, 1, 0, right? A times 0, 1, 0, that's going to pick up the second column, right? And so I get 1, 1, 0. right? 110 is the coordinate vector of e to the x plus x e to the x. Okay, so you see that, right? If I take x e to the x and I differentiate it, I get e to the x plus x e to the x. Okay, if I take the coordinate vector of it, 0, 1, 0, and I hit it with a, I get 1, 1, 0, which is the coordinate vector of x e to the x, I'm sorry, e to the x plus x e to the x. Okay, so this a does the same thing as differentiation, just in this sort of mirror world. Okay. Okay. Okay, let's see if we can get this one more thing. Okay, so remember what we did first. Recall, the first thing we did was take, we first took t from Rn to Rm and found a such that t sub a equal t. Okay. What if we use new bases, so different bases? What if we use different bases for Rn and Rm? Right? We use different bases E and F for Rn and Rm. So we can get a coordinate, we can get a matrix representation of T with respect to these new bases. Okay. Okay. So, right, so the picture is that we start off with T, like this, going from Rn to Rm, right? And what we did first was we found that we could actually represent this as some T sub a. Okay. Okay. Maybe I should not use this a. I'm going to use a different a. Use cursive a. But if we have bases over here, then we can do what we just did, and we'll get a different T sub a, right? We'll get a different T sub a. We'll get a matrix representation with respect to these bases, and that'll be a different matrix. So, yeah, so what we're doing right now, you could call, the matrix representation of T from Rn to Rm with respect to different bases. E and F. Okay. Right, the first thing we did was matrix representation of this, but not with respect to some bases. Yeah?
So you're not taking the coordinate, or you're not mapping it anymore? You're taking it with respect to E and F instead?
So it'll be a little bit funnier. We're going to take, you take your standard basis, right? No, I'm sorry. You take this new basis and then use its coordinate vector. Right, so you do exactly the same thing we just did, but with bases for Rn and Rm. So we're not actually doing anything unusual. It's just that we're going back just now we said, how do you get a matrix representation from some abstract vector space to another abstract vector space, right? And now what we're saying is that suppose those guys are Rn and Rm. Okay, and we'll see what happens. Okay. Okay. So here's the theorem. Going from Rn to Rm, you have a linear transformation, and you have some bases, V1 through Vn, and W1 through Wm. Then I claim that the matrix representation of T with respect to E and F is A1 through AN, where AI is TVI hit with the inverse of W1 through Wm. Okay, so I've kind of made a big deal about this, but it's actually not a big deal at all. Okay, all we're doing here is we're using the last thing we did in the case of Rn and Rm. Okay, that's all we're doing. So, right, the point is this, right? The point is this. From what we did before, from the previous work, AI, the ith column should be the coordinate vector of TVI with respect to F, right? That's what we said, right? The way you get the ith column of your matrix representation is to take the coordinate vector with respect to F of TVI, right? Okay. This size W1 to Wm. Okay. But how do you get the coordinate vector if you have a vector in Rm? If you have a coordinate vector in Rm, I'm sorry, if you have a vector in Rm, how do you get its coordinate vector with respect to a basis? Well, you just multiply, remember, you just multiply by, you take the basis elements and you put them into a matrix, and then you take the inverse matrix of that, and that gives you the coordinate vector. Do you remember that? We did this, I guess it's been a week, or it's been a couple weeks since we did this. So maybe you don't remember, but this is how you get it, right? To, right, recall, right? If to get the coordinate vectors, like if you have some v in Rn and you have a basis v1 to vn, then the coordinate vector of v with respect to the b basis, you just take your vector, and then hit it on the left with b1 to bn inverse, right? Okay, so, right, so this thing right here is just going to be, you take TVI, and then hit it on the left with the inverse of your matrix consisting of the F basis elements. So the point is that the first thing that we did when we entered this section was we saw that if you had a linear transformation from Rn to Rm, then actually that guy was left multiplication by some matrix, right? That guy was left multiplication by some matrix. Okay. Now, if we have bases here, then we have a different matrix. We have a different matrix representation with respect to those bases. Okay. And that matrix is not going to be the same as this one, right? It'll be some different matrix representation. Okay, and so depending on how you choose your basis, you're going to get a different matrix representation. Okay, let me do an example. Sorry, in the last minute, see if I can clear this up a little bit. So, okay, so this example I hope will be kind of cool. It's related to the Markov chain example that we did some months ago, weeks ago. So let M be 0.94, 0.2, 0.6, 0.98. Okay. Remember, this was the transition matrix for the city suburb problem. Okay. We're going to let U1 be 1, 3. We're going to let U2 be -1, 1. Okay. These were the vectors that we pulled out of nowhere, right? So let U, the basis U, consist of these two elements. Okay. And now let's ask, what's the matrix representation of M with respect to U on both sides? Okay. With respect to U on both sides. So we've got R2 to R2, right? M goes from R2 to R2, but we want a different matrix representation of it, right? We want an A so that this A represents the behavior of M. Okay? And how do we get it? Well, you take M of U1 and M of U2, right? M of U1 and M of U2 are 1, 3, and negative 0.92, 0.92. Okay. And then you hit those guys on the left by the inverse of this basis. Okay. So then, so you take 1, 3, negative 1, 1 inverse times 1, 3. You take 1, 3, negative 1, 1 inverse times negative 0.92, 0.92. And what you get is 1, 0, and 0.92. So A is going to be the matrix with those columns. Okay. So what this is saying is that, sorry, that's actually 0.02. 0.02. 0.6. 0.06. 0.98. Okay, so let me just say one last thing. What this is saying is that this was our original matrix, right? Multiplication by this matrix here. But if we change the basis, then in fact, our matrix is a lot simpler, right? Our matrix is a lot simpler. It's a diagonal matrix. And this is a trick that is going to be pretty useful to us, right? Change the basis to simplify the expression of the matrix. And then you can understand your transformation more easily. Okay, that's it for today.